Well, not just today, this week's going to be a busy week. Our goal is to finish chapter 13. That will take us up to 13.4. There's an awful lot still to go. You're going to be doing an awful lot of differentiation and integration and finding magnitudes of vectors, because that's basically what most of these things end up doing. In particular, we're going to just start at finding derivatives and integrals of space curves, just as a kind of overlap topic. And then we'll move on to the next section, 13.3. 13.3 deals with arc length and curvature. Also unit normal and unit vectors, tangent and unit binormal vectors. Although we have seen unit tangent, you haven't seen the other two yet. And then the last section, 13.4, deals with motion in space, which is basically velocity and acceleration vectors and how to calculate them and what do they mean. So let's get straight into basically, mostly for completeness sake, but here's a sine t, here's a 2 cosine t, here's an e to the t. If you want to find its derivative, you differentiate sine, differentiate cosine, and you differentiate e to the t, and you call it good. Nothing too amazing. Okay. Suppose I wanted to integrate that same function. Let's do it from 0 to say pi. Then you would integrate the sine function and the cosine and e to the t, and you do them all from 0 to pi. Well, if you integrate a sine, you get a negative cosine. You integrate a cosine, you get 2 sines. And if you integrate e to the t, you get this guy. And cosine of pi, well, let's see, -1. So negative 1 is 1. Take away the cosine of 0, which is 1, so 2. 0. And e to the pi, take away 1. And as processes go, really, all you do is differentiate 3 times, right, and integrate 3 times. We feel comfortable about those kinds of questions. I took very simple ones. I took essentially a couple of helixes because they're easy to do. What can go wrong? Well, the usual things that can go wrong. Couldn't you end up having to differentiate using a chain rule, a product rule, quotient rule, whatever? Can you have to sometimes integrate using u subs or integration by parts? Or you just end up having to integrate something you've forgotten what its integral is. I know it's early in the morning, but here goes. I'm going to keep battering on it with this one until everybody knows it. What's the integral of secant squared?
Tangent of t.
Yeah, are we all good at that now? Okay. So that was basically it. That was just a little overlap on 13.2. Has anyone come across any questions from, say, 13.1 or 13.2 that you'd like me to go over right now before we move on to arc length, which is in 13.3? Did anything weird happen to any question that you'd like me to go over?
There was space curves intersecting with paraboloids or whatever.
Right. Is the question you're talking about find where a space curve intersects a surface? A paraboloid is just one example of that. Is that the kind of question you're talking about? Or is it something else?
Let me look at it 1 second.
Okay.
Yeah, it was just the differing surfaces that they intersect with confused me a little bit.
So you want to, when does a space curve hit a paraboloid or whatever it might be called? Sure. Have you, hopefully you're still looking at the thing, have you got an example? Because if I make ones up, they'll be ugly, and if I use one of theirs, it'll probably come out nice.
So there's one that talks about the vector function between a paraboloid and a parabolic cylinder.
Okay, so you got the two equations, so z equals,
6x squared plus y squared.
right, and the other surface,
Y equals 4x squared.
okay. So, what the heck am I doing here? Well, you can't see what I'm doing. I'm trying to find something else. Okay, let's focus on our guys. Okay, so we got a guy like this. This fella here, I believe, looks something like that. Can you imagine the surface of like a cap going upwards? And y equals 4x squared. Well, if you draw 4x squared on the floor, and then you imagine it going upwards, it would look something like this. So evidently this shape and that shape, if you put one on top of the other, intersect on some type of curve. So the question is find the curve of intersection, or some phrase, something like that. Right, what you do in these questions is one of the two surfaces is only going to have two variables in it. If it has three variables, you're kind of screwed. So they can't give you it. Now, what I have here is the guy I'm going to start with. Y equals 4x squared. And I'm going to make x equals t, because I can make any variable anything I like. I have that much power. But if I make x equals t, which is just really a basic replacement, then won't that make y equal, instead of 4x squared, won't y now be 4t squared, because x is t? So the only guy that's left now is z, and we're finished. And typically, the one that's got the two equations generates two of the answers, and the third one, which used to be cx squared plus y squared, now becomes 6t squared plus y squared squared, which is 6t squared plus 16t to the 4. And so our space curve will be t, 4t squared, and 6t squared, plus 16t to the 4. We okay with that? So pick the equation that only has two variables. Choose one of them to be t. I would typically choose not the one that's the letter on its own, if there is such a guy, but the one that's actually got more stuff going on, in this case the x. Make it the t. The reason I'm choosing that is doesn't it make the y very easy? And once I've got x and y, I just plug them into here and we get z. Now you're occasionally going to have to deal with z squareds, in which case your answer will be the square root of this. It'll probably be the positive version, since we'll assume for some reason or other that it's only the top half of the surface curve that you want. Is there any other questions? Are we good about integrating and differentiation and intersections of two surfaces? Okay, I shall move on.
I think someone might be in the waiting room right now.
Oh, thank you. You know, I've mentioned this before, I don't actually get to see the same stuff that you get. So let me stop sharing for a minute and let that person in. Same thing is true. If someone's in the chat is asking a question, could you do the nice job of saying someone wants to know A, B, C, whatever it is? That would be helpful. Anybody wants to throw that in. Okay, so let's look at arc length in the three-dimensional space curve. Well, let's look at, well, let's try to imagine what arc length would look like. Well, can you imagine a space curve starting here at t equals a, and then it finishes up here at t equals b? If I was asking you to find the arc length, which is typically called L, wouldn't that be the distance along the curve from wherever t equals a is to wherever t equals b is, right? I think that is kind of intuitive, isn't it? There's my little space curve. If we do the analogy that that's a part of the roller coaster, if I started the roller coaster at this point and then it just stopped for some reason at that point, see the distance that I would travel? That would be called the arc length. Very similar to 2D arc length. Does anybody remember the formula for the 2D arc length? Not off the top of your head? Right, well, here we go. Suppose the space curve is given by the formula f of t, g of t, h of t, right? The usual standard space curve formula. Then the arc length would be the integral from t equals a to t equals b, the square root of the derivative of f squared plus the derivative of g squared plus the derivative of h squared dt. Does that look familiar? In the 2D world, wasn't it 1 plus the derivative f dashed x squared? And if you did it parametric, it would actually be that with a dt at the end. That's very interesting. Again, it's interesting because if that's how you get the arc length in 3D, couldn't you expand that formula to the arc length of a space curve in 10 dimensions? You probably start running short of letters of the alphabet, but you could do it. I'm not going to use this second version of the formula, although I believe this textbook might use it, so just in case you see it. It's just a naming device. I prefer to call this guy F, this guy G, and this guy H. You could describe this guy as a function X of t, a function Y of t, and a function Z of t. And if you did call that your space curve, then you see that would be your arc length. They are totally, completely equivalent in math. They're just placeholders for where you put stuff. You could call them any letter of the alphabet, couldn't you? I guess you could call it A of t, B of t, C of t, if you felt like it. And the formula wouldn't change. Well, let's do an arc length. I'm going to pick for my first one that helix. Then the arc length. Oh, I want to find the arc length of this fella from t equals 0 to t equals 5. Then the arc length will be the integral from 0 to 1. Okay, this fella is my f of t. If you differentiate him, you will get 3 cosine t's. And you square it. This is my g of t. You differentiate this, you get negative 3 sine t, and then you square it. And this is 4. When you differentiate it, you square it. Quite mechanical, isn't it? Just find a derivative, square it, find a derivative, square it, find a derivative and square it, add them all up. You can probably have a good guess at why I pick helix for my first question. This guy gets you 9 cos squared. The guy next door gets you 9 sine squared. And this guy gets you 16. Most integrations that involve the square root of things do not end well because they tend to be really ugly things to integrate, but not this time.
Shouldn't it be 5 to 0, not 1 to 0?
Did you all catch that deliberate mistake? He says, lying. Now, in this guy here, do you see that these two guys behave really nicely? Don't you just get 9? And 9 out of 16 is very nice. And you probably don't need this line, but I guess I'm just putting in because you may go back and you don't like skipped lines. You get that guy? Well, that's going to be basically 5t evaluated from t equals 0 to t equals 5. And so the arc length is 25.
Can you explain how you get to 25 from 5t?
Well, 5 times 5 is 25. Take away 5 times nothing. Right, you integrate 5, you get 5t, right? You substitute 5 here, you get 5 times 5, which is 25. Take away 5 times 0, which is 0. So you get 25. We're good?
Thank you.
Right. Now, the devil is in the detail. It's normally not going to be difficult to take these three things, differentiate them, and square them. The difficulty is going to probably arise somewhere here. This is one of the few examples, and I'm going to show you a second simple example in a minute, where this integral inside the square root becomes something very nice. Most of the time, this thing inside the square root is going to be ugly. And it's going to involve us having to do some sneaky algebra or substitution or some other process to get the exact value of this integral. But before we do that, let me show you a second nice example where this arc length comes out without too much trouble. Suppose I want to find the arc length of this space curve. And I want to find it from t equals 1 to t equals 2. Okay. Do you recognize this space curve? What shape would that be in 3D?
It's a line.
Yeah. So you can imagine finding the arc length of a line is basically quite simple, right? So it should come out easy, and it will. It's going to be the integral from 0 to 1, the square root of. Right, if you differentiate this fella, you just get 3 and then you square it. If you differentiate this guy, you get -2 and then you square it. If you differentiate this guy, you get 4 and then you square it.
It's the interval from 1 to 2, right?
No, it's not. It's the integral from 0 to 1. If I had a brain, I'd be dangerous. 9 add 4 add 16. So it's the square root of 29 dt. Now, do you notice that the final result, the thing inside this square root is a number? That makes life very easy, because isn't there a rule? It doesn't matter if that's 5 or the square root of 5. When you integrate it, don't you basically just add a t? Right. 5 gets you 5t, square root of 29 gets you square root of 29t. So it's going to be the square root of 29t evaluated at t equals 0 to t equals 1. And so my arc length is going to be the square root of 29. Because you plug in 1, you get the square root of 29. You plug in 0, you still get 0. Square root of 29. So far, so good? Right, now. I'm right now trying to find, and not being too successful, some examples of some more complicated versions of that same thing. So let's see if I can do that. Arc length. Now, the reason I kind of had to do this is I do not want to create a random space curve and try and do this process, because if I did, I could tell you right now what's going to happen. I'm going to end up with the integral of the square root of an ugly guy that is impossible to integrate. You know that square roots make integration very difficult. So you should only really pick, or you should only really be given questions where what ends up inside this square root is doable. And there are three main situations where it's doable. Number one is you end up getting the square root of numbers, right? That's doable, right? By that I mean, you know, imagine there's all that around it, but the square root of 15 is easy to integrate. 2, you get the square root of a perfect square. So the thing inside the square root ends up being, t squared plus 6t plus 9, something that can be turned into perfect square, because won't that basically cancel out and you'll just be left with what's left? And third situation is that you end up with a U sub situation, right? Something you can do a U sub. Technically, there's a fourth one, but God forbid if they ever do it. And what I mean by standard integrals is, do you know you can integrate the square root of t squared plus 1, but you go to the back of the book where they tell you, what is it, like 300 integrals, and they tell you what the integral of that guy is, right? God forbid you get that question, because it's a pain in the butt, because you have to go and look for somebody that looks like that to get it. So I hope the book keeps away from situation 4. So I now have a guy that that should work with. So I have a whole lot of interesting combinations here to do arc lengths on. Right, so number, you can't see it, number, this one. We would like to get the arc length of 2t, t squared, 1/3 t cubed. And I think I know what this one's going to end up doing, but I'm still going to use it. And you're going to do it from 0 to 1. Although halfway through that question, it may turn into 1 to 4. But apart from that, we'll be good. So its arc length is the integral from 0 to 1 of this guy. Okay, 2t gets you 2 when you differentiate it, and then you square it. This guy here gets you, what, 2t, and then you square it. And this guy here gets you t squared, and then you square it. And that's 4. And that's 4t squared. And that's t to the 4 dt. Now, for those of you who were hoping that when you got the situation that it's a nice perfect square, that you would get a perfect square that was a quadratic that you're comfortable with. And sometimes you will get that. This guy is a perfect square. So let me tell you why I know it's a perfect square. If you ever see 3 terms inside a square root and it's an arc length question, it's going to have to be a perfect square or you won't be able to do any more. That's just the bottom line. So if you are doing an arc length question and inside the square root there are 3 distinct terms, it is going to be a perfect square. So now the problem is, who is the perfect square? Any volunteers for what this is the perfect square of?
T squared plus 2.
Nailed it. Do you want to share how you recognised that? Because it might help other students who are still looking at that and wonder how you knew that. I mean, how did it come to your head?
The square root of 4 is 2, and 2 plus 2 is 4. So that got you your 4t squared and the 4 at the end. And then the t squared times t squared is t to the 4th.
Okay, So I can
I hope
paraphrase.
that helped.
Typically, you just need to look at the first and last term then, if I can restate what you said. Isn't 4 2 squared? Isn't t to the 4t squared? If that's going to be your perfect square, doesn't that have to be true? And then, do you know the guy in the middle just kind of falls, you know, it falls out because it has to, right? Right, now you do this guy, you now have the integral from 0 to 1 of that, because we'll assume that we're talking about positive numbers here, which we certainly are. And then you would have to move on to, can I just do a dot, 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 dot on that? Isn't that a Calc 2 thing? You know, 2t and a third t cubed and plug in some numbers. Okay. Imagine I did a different arc length question. And we got and that was the guy that we ended up with, right? So imagine a different question, we ended up with that. Right, it has to be a perfect square, agreed? Do you know that 6t cubed is an annoyance? It's probably better to pretend it isn't there for a minute. Don't you just focus on the biggest power and the smallest power? Now this guy here would get you t cubed. And this number here, wouldn't that get me 3? And there's your perfect square. So far, so good. Right. One last shot at this, and then we'll do another question. Another arc length question. Well, who cares what the numbers are? There's a weird looking guy. He has to be a perfect square. I've arranged them from the highest power of t, right, the biggest thing, to the smallest thing. What will 4t to the 4 generate? And that term goes there. What will 4t to the 4 give me?
2t squared.
Do you notice that you basically just take the square root of that term? Square rooting is half the powers as well. Now, be a little bit more careful about this guy. One over 4t to the 4. What would that get you? Well, you're drawing your fingers, it looks like that. What goes in the bottom?
T squared.
T squared. And then stick a plus in the middle, and you are good. And let's check that out. And if everything is correct, the middle term just kind of falls out. It just ends up working because it has to. Are you comfortable about how to take an ugly 3-term square root and make it a perfect square, because they have to be, or the question's not going to be doable? You comfortable with that process? Right. So let's choose another example of arc length. I'm just using some questions from the textbook, which I now thankfully have in front of me. And I just saw a really cool one, which I do not know what it's going to do. So that's always dangerous. we're going to find the arc length of square root, oh, excuse me, do that again, of the square root of 2t. So it's the square root of 2t, not the square root of 2t. There's a difference. And e to the t, and e to the negative t, and it's that 0, 1, which seems to be their favourite combination in t values. So it's going to be the integral from 0 to 1. Right, if you take this guy and you differentiate him, you will get the square root of 2, and then you square it. Okay, I can live with that. If you differentiate this guy, you get e to the t, then you square it. And if you do this guy, you get negative e to the negative t, and then you square it. So far, so good. It's going to be the integral from 0 to 1. Okay, the square root of 2 when you square it just gets you 2. Okay, here's some algebra. E to the t squared. Is it e to the t squared or e to the 2t? Only one of them's right.
E to the 2t.
Agreed. And this one here, you will get e to the negative 2t. Now, it's got 3 terms, agreed, which makes it a perfect square. But you don't just write them down or use them in the order they just happen to appear here. The trick to doing the first guy and the last guy is to make sure that the first guy is the biggest thing and the last guy is the smallest. So what I mean by that in this case is that the first guy is e to the 2t, because for most values of t, isn't e to the 2t going to be the biggest answer? Think of 1 billion if you need a number to work with, right? Okay, done. Which term is, of the 2 that are left, which is the next biggest? Or the middle one, if you prefer?
Two.
And that makes this guy the third one. Won't negative powers be the same thing as 1 over e to the 2t? And isn't 1 over the e to the 2t going to be really small, especially when t is 1 billion? So now that they are in order, we can do that little algebra trick of saying, I know that you have to be a perfect square, and you are. And I know that this guy, if I take its square root, will get me e to the t. And I know if you take this guy and you take his square root, won't you get e to the negative t? And can you trust me that if you FOIL this out, you will get 2 in the middle? Kind of cool magic, isn't it? That you're factoring perfect squares for things that you've probably never needed to factor in your life before. Almost the vast majority of your factoring has been trinomials, right? T, x squared plus 4x plus 4, those kind of things, right? And perfect squares in those worlds are very easy to see, aren't they? But now we're moving into the algebra world of any 3 terms inside the square root of this kind is going to be a perfect square, which means that we now have the integral from 0 to 1 of e to the t, e to the negative t, dt, and I'll dot that, because you could all finish that in your own time. Now, we've looked at arc lengths where this is just a nice number, right? Arc length where it's a square root of 4, square root of 10. We've looked at arc lengths where the thing you got is a perfect square, right? Now I'm going to go hunting for an arc length question where you have to do a use up. And You can't see what I'm doing right now. I'm looking at various questions. They only have 9 that I can work with. And I'm trying to see if I can see one in this 9 that'll end up being a U-sub story. Okay, this is probably not it, but it's the closest one I can think of. We're being asked to do a space curve that's cosine t, sine t, and followed by the natural log of the cosine of t. So I'm picking this one. Oh, a little bit different. 0 to pi upon 4. So it's going to be the integral from 0 to pi upon 4. Okay, let's see what we get. These two shouldn't be an issue. You differentiate a cosine, you'll get a negative sign. Then you square it. You differentiate the sine, you get a cosine. Then you square it. Okay, yikes. If you differentiate the natural log of 1 over cosine t, don't you get 1 over cosine t times the derivative of cosine t, which is what, negative sine t? So you're going to get negative sine t on the top over cosine t, and then don't forget to square it. So it's going to be the integral from 0 to pi upon 4 of sine squared t, cos squared t. Isn't sine t over cosine t tangent? And so that's going to get me tangent squared. Oh, I see where this one's going. Oh, I didn't put this down as my list of things that could happen because I never thought about it. Superficially, that's impossible because it's a square root with 2 things inside it. Can you trust me that a U-sub's probably not the way to go? So this is not a U-sub question. But there is a way that this guy can go. There is a pathway to the solution.
You're going to turn it into secant squared, and then it just becomes secant.
The integral of secant t is not secant tan. That's what the derivative of it is. The integral of secant t is a standard integral that you will get at the back of the book. And it's something ugly like secant t plus a natural log of secant t tan t or something, right? So you just go look up the back of the book and you bite the bullet and you write down whatever it tells you. So that's what the answer to that one would be. I don't know if I'm going to get what I wanted. The 2 other examples that I'm looking at I know are perfect squares. Oh, this one, last attempt. I'm trying to get one that is a U-sub. And so this is my last attempt at it. If I can't get one, it's because the book has decided that it didn't want me to get one. Whoops. This guy, between 0 and 2, doesn't look too scary. Differentiate this guy, you get 2t and then you square it. Differentiate this guy, you get 3t squared and then you square it. Differentiate this guy. Oh. and then you square it. Four t squared plus 9t to the 4 plus 16t to the 6 dt. Do you know this question could have been a U-sub question if the textbook had given it a little bit more thought? And I'll show you how I would at least approach it. But the book doesn't. The book says, use your calculator and give the answer to 2 decimal places. So do you know that you just can plug this guy into your calculator? You don't use your calculator to get the numerical integral, right? You plug this guy, call it x's, and then you put 0 and 2 in it. But let's continue as if it was going to be a perfect square. It does have 3 terms in it, but it's not a perfect square. I can tell you that right now. But do you notice that they share a common factor of t squared? So I would pull out the t squared. I could then separate that as the square root of this and that, and I'd end up with this fella. Now, if they had designed the question in a better format, couldn't this fella here have been something that you do a U-sub on and get this guy? In other words, if this had been done in a better format, or something like that, like 4 plus 9t squared, couldn't that have been a U-sub question? You can't win them all. So evidently, there are no situations, at least none that I can find, where the square root question gets solved by doing U-subs. There are lots of questions where it gets solved by being perfect squares or trig identity, but nothing else. Before we move on, if I give you a question and I ask you to find the arc length of a space curve from 0 to 2, do you feel comfortable about the math of what you're going to do? Would you agree most of it is Calc 2 single integral with horrible algebra? And the horrible algebra tends to be making things perfect squares for the most part. If you're really lucky, it's a number. If it's not, perfect square seems to be the way to go. Are we good? Can I move on? The next topic that we're going to deal with today is called curvature. Imagine a space curve in 3D, and you start here, and you know, maybe you finish there, and space curve does its thing. There is a concept called curvature, which, for want of a better word, is how curved is your curve? Now you might think, what are you talking about? Well, can you imagine a space curve at this point here had that kind of curve to it? And then there's another space curve with that kind of curve to it. And there's another space curve with that kind of curve to it. In some kind of intuitive way, at this point here on the curve, isn't it not very curved? It's almost straight. This guy here is kind of middle of the road. It's got a little bit of curvature going on. And at this point here, isn't there a lot of curvature going on? So can you visualize what I mean when I say how curved is a space curve, or how curved is a vector function? Maybe I should use vector function so we don't have two curves. Now imagine you wanted to put a number on how these vector functions are curved. And you might think, how did they do it? Well, let's start off with a shape that we all like. Would you agree that a circle is probably a good example of a shape that's got the same curvature everywhere? And if you look at a circle and you take a big circle and you take a small circle and you take a tiny circle, would you agree that this one is a very gentle curve? Your change in direction is quite small. So this would have small curvature. Wouldn't this tiny little one, can you imagine that you're curving really fast, right? You're going round a bend on two wheels if you tried that one. And this would have a very big curvature, and this would be in the middle. And we use a Greek letter that looks like a K, but it's actually the Greek letter kappa. And kappa is the curvature. So if this circle had a radius of 10, then its curvature is 1 over its radius. It's a tenth. If this one here had a radius of 1/4, then its curvature is 1 over its radius. Its curvature, kappa, would be 4. And this guy in the middle, I don't know, maybe his radius is 3, so his curvature would be a third. So kappa, the curvature, is 1 over the radius of a circle. Well, how can I use the measurements for circles curvature and apply them to normal space curves? Well, what you do is, suppose I was interested in the curvature of this point here. Can you imagine that I could get an infinite number of circles, but I could match one circle that at that point there was the same curvature as my space curve. So you can imagine at one point on a space curve, there's a little curve thing going on. Couldn't you go through all your circles, bigger, smaller, move them around, move them up and down? But eventually, there's a unique circle, trust me. There's a unique circle that has the curvature of that. And that is described as the curvature of a space curve. You imagine a circle with the same curvature at that point, and 1 over the radius of that circle. So in this case, can you imagine that circle having a radius of r? Then the curvature would be 1 over the radius of that circle. So I'm just giving you the geometric explanation of what the curvature means to any space curve. It's 1 over the radius of a circle with the same curvature. And can you imagine that as you travel along a space curve, won't the circles change shape? Won't you get big circles somewhere because it's not very curved, and tiny little circles because it's bending really quickly? So at any given point on a space curve, won't the curvature change? So let's look at special cases. Suppose you had a straight line. What would the curvature of every single point be?
0.
Would you agree that you can't get anything less curved than a straight line? Right, that's pretty much the ultimate of not being curved. Now you might think, well, how does my weird definition of circle work? Technically it still works. What size circle would you need to be straight at the end?
An infinite one.
And wouldn't 1 over infinity get you 0?
No.
Yes, in the context of 1 over the limit of an infinite thing would be 0. How about phrasing it that way? Agreed?
Okay.
Okay. Now, suppose my space curve happened to be a circle. And that circle just happened to have a radius of 5. Based on what I've said earlier, what would the curvature of that fella be?
1/5.
In fact, wouldn't it be 1/5 on every single point? Now, I'm not going to do this very well. Imagine you had a helix. Now, it could go vertical upwards, but actually it doesn't matter. Do you know that the helix, every single point on the helix has the same curvature? It does. Every single point. Now, your orientation may make you think that it's, you know, more curved or less curved at certain points, but it actually isn't. If you rotate the shape a bit and you look at it from above or sideways, whatever you want, it looks different. But really, at any given point, the curvature is the same. If you take a helix, can you imagine a central spine going through it? At that point there, do you know that you've just basically got a circle? Or at least the curvature of a circle. And if this was 2, then for a helix, the curvature is a fixed point. Now, what that is telling me is that there are more shapes in the universe than just circles that have the property that every point has the same curvature. Helixes, for instance, have the same property as a boring circle. You know, that could be a circle in 2D, but it wouldn't really be going very far. At least a helix travels. Last weird special case, a single point in space. So I guess that would be, you know, a space curve that looked like this. Wouldn't that just be one point in space, the point with coordinates 1, 2, 3? If this definition is going to work, we have to cope with all extremes. Well, at one extreme, you've got a curvature of 0, which is what straight lines give you. Here's the other extreme, a single point. How much curvature has that thing got? And it's not 0.
Since it's the other extreme, I'm guessing it's going to be k equals 1. Oh, infinity.
Okay, why? Where's my calculation that's generating that? Remember that it's 1 over the radius of the circle. If you've got a point in space, technically, I wouldn't call it a circle, but isn't r equals 0 is the only way you're going to get it? But if r equals 0, isn't 1 over 0 going to get me infinity? Or the limit as the thing tends to 0 is going to be infinity. And curvatures are always positive. You don't get negative numbers in curvature, right? So that's the theory behind what curvature is. So when we do questions, as we're about to do in a few minutes from now, and I find that in this space curve at t equals 2, the curvature is 5, Can you just imagine what a circle would generate that? Well, the circle would have to have a radius of 1 over. So if you switch that the other way round, isn't 1 over the curvature the circle that would have the same curvature as you? That's the radius of it. Right. So that's what we're getting. So what does the formula look like? Not pretty. So here is one of the two formula. Suppose we have that function, and I would like to find the curvature at any given value of t. And no, I am not going to prove this. This isn't the final part. This is only a piece of the formula. You find the first derivative and you do a cross product with its second derivative, which, if you're interested in motion, isn't that the cross product of velocity with acceleration? And then you find the magnitude of that vector. So that means you're going to get a scalar. And if that wasn't weird enough, you then divide by this guy cubed. Can you see why I'm not even going to attempt to prove that to you? God, I would hate to. I can't even remember when I was at university if that ever get proved. If it did, my brain probably blocked it out because it would probably take about half an hour and 12 pages. I'm guessing. I couldn't even think where to start to prove that. But shall we take it as magic, and we'll just live with it. So if you give me a space curve, I'm going to find its first derivative, I'm going to find its second derivative, I'm going to do the cross product of those things, and then I'm going to divide by the magnitude of the derivative vector cubed. Well, since this is going to be a really big and ugly question, I am going to make my life easy, and in a way, hopefully making your life easy. I am going to find the curvature of that guy. Do you recognize that? I'll get that again. Do you recognize that this guy is essentially? Oh, sorry. Do you recognize that this guy, I put the 1 in 2 places, is a helix? Which axis is this helix spiraling upwards? Right, it's going up the z-axis, isn't it? If you imagine what the shape might look like, it would look like this. If you were in the z-axis looking downwards, wouldn't you just basically see a circle? Agreed? If you cover up this term, do you see 3 sine t, 3 cosine t? You see that guy there? Do you know that the radius of this circle is 3? So I'm making a prediction here. That the curvature of this helix is going to be 1/3, and it's going to be totally independent of t. In other words, it doesn't matter what point on this helix that you do, you get the same curvature. That's my prediction. Okay, let's do the math then. First derivative, 3 cosine t, -3 sine t, 2. Are we comfortable with what I just did there? Now, I need a couple of things here. Basically, don't I need to know the second derivative so I can do the cross product? So what I'm going to do now is find the second derivative. So if you differentiate this guy, you get -3 sine t. If you differentiate this guy, you get -3 cosine t. And if you differentiate this guy, don't you get 0? Can you predict or imagine that this process of calculating curvature can quite easily get out of control if this function, the original one, isn't relatively simple, right? If you started just randomly picking weird stuff for F, G, and H, can you imagine this could turn into a half-hour question? Right, so keep it simple is the goal of the questions we're going to do so that we can get used to the process. I strongly suspect that the book knows that, and so that when you get to do these curvature questions, you'll get things like helixes and maybe a straight line, you know, something that's not going to be too onerous on the brain. Right, well, now I need to find the cross product of those two guys. So we're going to have an I, we're going to have a J, we're going to have a K, and the first guy is going to be 3 cosine t, -3 sine t, and a 2. And the next guy is going to be -3 sine t, -3 cosine t, and 0. Now, do you notice that we're going to be doing cross product where the terms are not numbers, where the terms are actually expressions with t in it? Can you imagine that that itself is going to cause some calculation issues? It's going to be a little bit harder to do, but we should be able to do it. It's going to be so many i's, take away so many j's, plus so many k's. Okay. If you cover this guy up, don't you get 0? Take away -6 cosines, so that means +6 cosines. I'll do the middle number now. Don't you get 0? Take away that negatives, take away a negative gets you positive. And if you do this one, if you multiply these two together, don't you get -9 cos squared? You agree? -9 cos squared. Take away 9 sine squared. So what would 9 cos squareds minus 9 sine squareds get you? It's actually a number. What would -9 cos squared, -9 sine squared get you? What number would that get you?
Is it -9?
Yeah. We're all used to sine squared plus cos squared as 1, but isn't any multiple of them also going to get you a number? Right, 5 sine squared plus 5 cos squared is going to get you 5, and -9 sine squared, -9 cos squared is going to get you -9, right? They all work. Now that fella there, I'll put him up here now. Ends up being 6 cosines, -6 sines, -9. So that's this piece done. What we now have to do is find the magnitude of this vector, right? The magnitude of this vector. Well, to get the magnitude of a vector, don't you basically take its components, square them, and add? 36 cos squareds. That's positive. 36 sine squareds. What does 36 sine squared plus 36 cos squared get me then? Thirty-six sine squared plus 36 cos squareds.
Wouldn't it just be 36?
Yep. See, the more times it happens, the quicker that question will get answered. So you put this together. Oh God, would you look at those horrible numbers? 111. I think it's 117. I got a thumbs up on that. Doesn't look too promising, does it? Well, I still got a bit to go. Don't I need to find the magnitude of the first derivative and then cube that answer? Right. I'll take it in small chunks. Let's find the magnitude of it. Well, that's going to be the square root of this guy squared plus this guy squared plus 2 squared. So that's going to be the square root of 9 cos squareds plus 9 sine squareds plus 4. Okay, what's 9 cos squared plus 9 sine squared going to get me?
9.
Ah, see, it was faster. And 9 add 4 gets me 13. So I get the square root of 13, don't I? And so I don't have to rewrite a whole load of stuff. Can I stick a cube on that? Which simplifies out, if you call it simplified, to that guy, right? Now I'm ready to put those pieces together. And I am crossing my fingers like nobody's business to make sure I haven't screwed up. So here goes. The curvature at any given value of t is the magnitude of the cross product of those two guys divided by the magnitude of the first derivative cubed. That top guy ends up being the square root of 117, and that bottom guy ends up being this fella. And 117 divided by 13 gets you 9. Okay. 9? Okay, my cap is wrong. This guy divides this guy, you get the square root of 9 over 13. You get 3 over 13. I think I must have just made a mistake here when I was doing my calculation. But at least, isn't it a fixed number? It doesn't depend on t. So my idea that it is got the same curvature as a circle is correct. I just didn't calculate the r value probably correctly. God, that's work, isn't it? And believe it or not, that was the easy one. Well, I guess the easiest one's a straight line. But a straight line's going to get me 0, so I'm not going to really do that one. Because, I mean, it'll disappear. So we are going to have to look for the curvature of another example of this guy. But I'm going to at least make my life a little bit easier, because I'm only going to find the curvature at one given point. That does reduce the math quite a bit. So since I am going to do that, I can actually be as generous as I like with the function and it won't matter. So suppose we have a t to the 4, a t squared, and a 5t plus 1. Would you agree that's just a pretty boring curve, who knows where the heck it goes, right? So at any given value of t, that is going to have a totally different curvature to any other given point, probably. But let's suppose I'm only interested in the curvature at 1. Right, so that means the curvature at t equals 1. So you might say, well, how is that going to reduce our workload? It will, quite substantially. So I'll start off by finding the first derivative, which is 4t cubed, 2t and 5. Isn't too painful. And then I will find the second derivative, which in this case is 12t squared, 2 and 0. So far, so good. But since I am only interested in the curvature at 1, can't I now evaluate these at 1 and have numbers to work with, which tends to make life so much easier. So this guy is 4, 2, 5. And this guy is going to be 12, 2, and 0. Which means that the cross product is really just going to be much easier to handle. 4, 2, 5, 12, 2, 0. And let's see what we get. So many i's. Take away so many j's. Plus so many k's. Okay, cover that guy up. Nothing, take away 10. It's negative 10. Cover up the middle guy. Nothing, take away 60 is negative 60. Cover up that guy. 8 take away 24 is what, negative 16. So we end up with the vector negative 10, positive 60, 16. So the magnitude of the cross product,
Might be minus 16.
this one here, thank you, is going to be this guy squared, that guy squared, this guy squared, and that's why we have calculators, right? So what am I going to get? I'm going to get, well, I guess I should put this in since this is for notes. 100, 3600, and 256. You should all be amazed that I could actually do that in my head and do it correctly. 3600, add 100, add 256, and I'm getting the square root of 3956. Okay, now this fella was 4, 2, 5. So the magnitude of this fella is the square root of 4, 2, 5 squared. So let's see what that gets me. That gets me 16, add 4, add 25, which is the square root of 45. And then if you cube it, you get 45 square root of 45. So the curvature of this fella at t equals 1 is given by this fella divided by this fella. So 3956 over 45 square root of 45. If there's any chance, and I doubt it's going to happen, won't this might divide into that and it'll tidy up a little bit. I suspect strongly it's not, but I'll just do it just in case. 3956, if you divide it by 45, doesn't work. So can you imagine that's the answer? You could tidy it up a little bit by rationalizing the denominator. I'm not saying it would do much good, but at least the 45s would cancel. Oh, I take that back. Do you know if you multiply top and bottom by that fella? Yeah, nah, it's still ugly. I thought it might be nicer, but it's not. As long as they give you a single value, like at 0 or at 1 or something like that, won't this curvature, I mean, it's quite a long question, but at least it's not that bad on algebra. If they kept this guy at t, can you imagine how ridiculously ugly the math here would be? But what it would allow you to do then is to, once you've finished with it, you'd have this big ugly formula with t's and square roots of t cubes and who knows what else. But once you've got that formula, couldn't you find a curvature at any given point? You know, just plug t equals 1 and you get the answer at that point. And if you had a curve, right, a big ugly formula. So imagine you had a curvature like this, and it's a big ugly formula, right? It's got t cubes and square roots of stuff and all sorts of it, right? Suppose you had this formula for the curvature at any given fault t, right? And it's a big ugly guy, right? Could you imagine that there might be at least one point, some value of t that gives you a curvature of 0? Can you imagine that happening? What is happening to a curve when that happens?
It's
It's
flat.
a straight line.
Well, a straight line, yeah. So can you imagine that you have a space curve? None of these are very straight, but can you imagine that you might have a space curve for where part of its life, it was straight, as in a straight line. What kind of thing might do that? I don't know. Do you know if you shoot a rocket up into space, see when it leaves Earth, it could be quite linear at the beginning, couldn't it? Before it starts doing its orbiting thing. So I could imagine a space curve modeling the trajectory of a rocket. When it leaves the Earth, at least it is quite linear, isn't it? It's vertically upwards. You can't get much linear than straight up, right? Yeah. This is even weirder. Suppose you had a model for the movement of an object, right, a space curve, and its curvature was infinity at a given point. Now, I could make infinity happen. Can you imagine that the curvature function was t squared plus 1, maybe even a square root around it, right? All over t minus 1. Right, something like that. Can you imagine what would happen at t equals 1? Couldn't the curvature be infinite? Okay, that one's a little bit harder to imagine. I can imagine, you know, a space curve being linear and having 0 curvature at certain places along its life. What do you think an infinite curvature would look like? What would be happening at the curve at t equals 1 in this case? No thought process comes to mind.
Wouldn't there just be like a hole there at t equals 1?
Yeah. Can you imagine an object traveling through space and getting sucked up by a black hole? You know, a singularity. It's bye-bye to space curve, isn't it? So you could, I guess you could be modeling the pathway that an object would make as it travels towards a black hole. It would have quite an interesting space curve. I think at the end of its life, if I know anything about black holes, is that you don't shoot right into them like a bullet gets shot onto a target. When you get close to it, apart from getting stretched to spaghetti, amongst other things, don't you actually theoretically spiral down into the event horizon and then you're gone? So I can imagine this poor little object as it travels through space in its space curve. The model would say that you're traveling quite nice, and then towards the end of your life, wouldn't you do a spiral of death, finishing up with an infinite singularity? Because basically, I believe at least the theory says that when you're in a black hole, don't you get crushed to a singularity, a single non-moving point in space. So, if you're interested, that would be it. These fellas take a fair chunk of time, as you've probably already noticed. I'm wondering if I should probably pause at this moment and go and look at our homework. And that way I can see what kind of quality of questions. I should have looked at. I never do. What theirs looks like. And if I come across an interesting one, I'll do that as our next question. So if you could wait patiently for a few minutes. It's 13.3. I'll do a quick view on it. There are 12 questions. Find the length of the curve. Nothing interesting going on there. Unit tangent normal. Haven't done that yet. How boring can you get? Oh. Yeah. There is nothing weird and wonderful. I'll just show you what I'm looking at, just so that you can hopefully agree with me. I'm just looking at the homework questions that you've got. I think there's 2 of them altogether, so it's not like, I mean, it took me for ages just to show you how you do 2 questions, so it is what it is. Right, you should be looking at the same stuff I'm looking at, right? Okay. Yeah. Oh, that's not good. Can you still see me? Because I'm saying Zoom quite unexpectedly. I am not going to close that window in case Zoom disappears on us. So we are going to stay here. Are you looking at the solutions?
Yes.
Okay, thank goodness for that. Right, now I'm just going to go and talk us through some of these questions. Question 1, isn't that basically a, oh, those answers distract the heck out of me. Right, here we go. Find the length of a curve from -5 to 5, another arc length. Some basic arc lengths, right? Now, question 5 is a little bit different. X squared equals 2y and the surface z, 3z equals xy. So the first part of that process, and I'm actually going to do this one, you have a surface x squared equals 2y, and it's meeting up with another surface that has a formula 3z equals xy. And we're being asked to find the length of the curve from the origin to the point 5, 25 halves, and 125/6. Okay, Travis, you have a question.
Sorry, I got booted out of class for a little bit earlier, and I was just wondering if you took attendance.
I haven't, but now that you've mentioned that, as soon as I finish this question, I will take attendance in case I forget. So no, I didn't take attendance. Okay, so you can't see what I'm writing, but I'm basically writing this question, and according to them, I better get 155.6 when I'm finished. Okay, so that's the next question I'll do, but before we do that, forget about these, we haven't covered them yet, but here's a space curve, get its curvature. Can you recognize that that's a helix, so it's going to be a nice number? This fella here, I think I'll make him my second question then. It's 3t squared. There's a sine t. No, there isn't. I can't read. Okay. We have a 3t squared, a sine t take away t cosine t, and a cosine t add a t sine t. And I am going to get the curvature of that. Okay, so I've now got two questions that we're going to do, or at least I'll try. If we get through them, that's great. All right, anything in the chat? Typing in something. Okay. Right, first question was asking for an arc length, but it wasn't asking where was it going? It wasn't asking us straight off the bat. It wasn't telling us, here's r of t, find the arc length, you know, from t equals 0 to t equals 2. So let's see what they did have. They had a surface that intersected with another surface. And I'll call this equation 1 and I'll call this equation 2. So I have to generate the RT from scratch. So that's what makes it a little bit different from the usual arc length question. Now, right at the beginning of today, didn't we do a question very similar to this? So which one of these two equations should I start with?
X squared equals 2y.
And the reason I choose that one is because it has two variables, right? Now, I got to pick one of those two guys, and it really doesn't matter, but try and make your life easy, right? I'm going to pick one of these guys to be t. And I'm going to go that road. Could you have made y equals t? Sure you could, but wouldn't that make your life harder because you'd end up with square roots? Now, if I make x equals t, then won't 2y be t squared? Which means y will be a half t squared. I can live with a half t squared, right? Now, if I go down here, 3z equals xy, well, won't that make 3z equal t times a half t squared? Won't that make 3z 1/2 t cubed? So won't that make z 1/6 of t cubed? Would you agree that's probably the nicest version that you're going to get? If I tried any other choice, I'm probably going to get some weirder stuff. So that gives me the point t, that gives me a half t squared, and that gets me 1/6 t cubed. And we are going to be finding the arc length from the origin to the point 5, 25 over 2, 125 over 6. Well, here's my second problem. If I'm going to do an arc length, doesn't it have to be t equals 0 to t equals 4, right? That kind of thing. But I don't have t equals 0 to t equals 4. I have this point to that point. But I can figure out who the t's are. Didn't I make x equal t? Agreed? So what value of t would get me an origin?
0.
Don't you basically just say x is t, x is 0, therefore t is 0. Now, x equals t, x equals 5, therefore t equals 5. Do you see how I converted those 2 points into the corresponding t values? Right. Now you're going to put this package together. So the arc length is going to be the integral from 0 to 5, the square root of this guy's derivative squared, plus this guy's derivative squared, plus that guy's derivative squared. So it's going to be the integral from 0 to 5 of a 1 plus a t squared plus 1/4 t to the 4 dt. And now I feel much nicer. I was kind of when I saw this, but I'm happy. This guy has got 3 guys inside it. If there's 3 guys inside it, isn't it going to have to be a perfect square or this question's finished? And since it is going to be a perfect square, and I guess I could rearrange it big, middle, small, but aren't they okay, small, middle, big? You can have it both ways round. So won't this guy get me 1? And won't this guy get me a half t squared? And you can check that out, but that guy is this guy. Perfect square. And that's going to be giving me the integral of that guy. And then I'll ... Right, you finish it in the usual way. That's a cool question. But do you know how hard it must be to create a question that came out so nice? I mean, if I just randomly pick 2 surfaces, what's the chances that those 2 surfaces end up giving me a relatively pretty intersection curve, right? And then that itself ends up generating a perfect square. That is a lot of clever math for the person who created that question, but not me. Are we good with that one? Right, now, how much time have we got left? I don't think we have enough, do we? Yeah. Okay, someone with a really good memory, which is not me, is going to remind me tomorrow that we're going to do question 7. That's probably the easiest bit, right? And what basically 7 is going to be is that we're going to do the curvature of this ugly guy. And when I see you tomorrow, then that'll be the last kind of guy that we'll do. That's like curvatures kind of done. And then we'll look at the unit tangent normal and unit binormal, right? And that is us. So don't go.